Let's take a look at matrix multiplication. We know most of what we need to know about matrix multiplication already. Matrix multiplication is going to be an extension of multiplying a matrix by a vector. So this is going to be an extension of multiplying a matrix by a vector. So the way it works is if I have a matrix A, let's let A be an M by N matrix. And I'm going to multiply it by a matrix B. So B has to have the same number of rows as A. So let's let B be an N by P matrix. So once again, the number of rows of B must equal the number of columns of A for the multiplication to be defined. So the number of columns of A must equal the number of rows of B for AB to be defined. If the number of columns of A is not equal to the number of rows of B, then AB is not defined. Full stop, all done. Don't even worry about it. So I'm also going to name the columns of B. So let's let B be an N by P matrix. And the column, that's a weird looking B, where B, and the columns are just going to be B1, and it says apparently there are N rows and P columns, so B1 up to BP. So I'm just going to name the columns of B. Not going to worry about naming the columns of A. The columns of A, the product AB, are just going to be linear combinations of the columns of A using the entries in the columns of B as weights. AB is just, the first column of AB is just going to be A times B1, then A times B2, to A times BP. So we're just multiplying a matrix by a vector a bunch of times. It's just an extension of multiplying a matrix by a vector. So if I have a matrix A, there's no way I could come up with a matrix on the fly, because that would mean coming up with a bunch of numbers all at once. And we know that I can't do that. That's not what I want to look at. Let's take a look at let's see. Let's suppose that I have a matrix A is going to be 2, 0, -1, and 1, -4, -3 by columns. So first column is 2, 0, -1. Second column is 1, -4, -3. And let's let B equal a 2 by 2 matrix. So 3, -1, 5, 4. So let's look at an example where A is by columns 2, 0, -1, 1, -4, -3, and B is 2 by 2. By columns is 3, -1, and 5, 4. So if I want to multiply the matrices, first of all, I should check if the product is going to even be defined. A is 3 by 2, B is 2 by 2, so my product is defined, and the result will be a 3 by 2 matrix. So A is 3 by 2, and B is 2 by 2. Since the number of columns of A is equal to the number of rows of B, AB is defined and AB will be 3 by 2. That'll just be the things on the outside. Oops, that's a bad highlight color. Notice if I wanted to turn this around and I wanted to multiply B times A, that's not defined because B has 2 columns and A has 3 rows. So to do this product, I have 2, 0, -1, and 1, -4, -3. And I'm going to multiply this by 3, -1, and 5, 4. So the first column of the product is going to be a linear combination of the columns of A using the entries in B as weights. So the first column of the product AB will be 3 times the first 3 times 2, 0, -1 minus 1 times 1, -4, -3. That's the first column of the product. Then the second column of the product will be a linear combination of the columns of A using the second column of B as weights. So 5 times 2, 0, -1 plus 4 times 1, -4, -3. So here is A times B1, and here is A times B2. So if I name these vectors B1, the columns, if I name the columns of B as B1 and B2, this first column is going to be A times B1, and the second column is A times B2. Now let's write out what this means. So what I get, this first entry here is going to be 3 times 2 minus 1 times 1. So 3 times 2 minus 1 times 1. Then I'm going to have 3 times 0 minus 1 times -4. Then I'm going to have 3 times -1 minus 1 times -3. And then the second column, I'm going to have 5 times 2 plus 4 times 1, and then 5 times 0 plus 4 times -4. And then the third entry in the second column of AB will be 5 times -1 plus 4 times -3. And this shows us the row column style of multiplication. I'm making dot products. I'm doing a dot product of the first row of A times and the first column of B, for those of you familiar with dot products. For those of you who are unfamiliar with dot products, they're still dot products. You're just not sure what a dot product is. So I'm doing row column, 2 times 3 plus 1 times -1. 0 times 3 plus -4 times -1. -1 times 3 plus -3 times -1. So row and column. And then that gets us to our product if I just work all these details out. So 6 minus 1 is 5. 0 plus 4 is 4. -3 plus 3 is 0. Then in the next column of AB, I get 10 plus 4 is 14. 0 minus 16 is minus 16. And -5 minus 12 is -17. Assuming that I did my adding and multiplying correctly, which is not a good assumption to make. I'm terrible at arithmetic. Any questions? So there's a couple of things going on. There's how we want to think about matrix multiplication. We're making linear, to find AB, we're making a linear combination of the columns of A using the entries in each column of B as weights, making a linear combination of the columns of A with the entries in B1 as weights. Then the second column will be the linear combination of the columns of A using the entries in B2 as weights. We want to think about it in terms of multiplying rows of A by columns of B. 2 times 3 minus 1 times 1. 2 times 5 plus 1 times 4, and so on. So rows of A times columns of B. That would be a shorthand way of thinking about it. Down here, we're thinking rows of A dot column of B. Dot product. You find the dot product of a row of A and a column of B. And those will be the columns of AB. So that's how matrix multiplication works. You'll notice that I didn't talk about scalar multiplication by a matrix by a scalar. I didn't talk about multiplying a matrix by a scalar. I also didn't talk about adding matrices, because I'm just going to ask that you guess how that's going to work and then verify that is indeed how it works. The reason that we're pointing out matrix multiplication is that matrix multiplication does not work how we might guess it works. So that's why we have to talk about it. Any questions? There's another thing that we spend a lot of time thinking about when we're dealing with matrices and matrix multiplication. So let's talk about the inverse of a matrix. And the inverse that we're talking about is an inverse under matrix multiplication. So when we talk about the inverse of a matrix, we are talking about the inverse of a matrix under multiplication. So inverse is a general term. If we're talking about real numbers, we have an additive inverse, which we call the opposite, and we have a multiplicative inverse, which we call the reciprocal. So the inverse of a matrix is kind of like the reciprocal of a matrix, although don't say it that way. It's the inverse of a matrix, and it's implied that we're talking about the inverse under matrix multiplication. If we're talking about the inverse under matrix multiplication, that is, if we're questioning whether a matrix has a multiplicative inverse, there has to be a multiplicative identity. So the identity matrix. Which we'll usually abbreviate as IN. It's I sub n. So the n by n identity matrix, IN, has ones on the main diagonal and zeros elsewhere. So we'll have ones on the main diagonal and zeros elsewhere. So I2 will be 1, 0, 0, 1. That was by columns. By rows, 1, 0, 0, 1. I3, the 3 by 3 identity matrix, will be 1, 0, 0, 0, 1, 0, 0, 0, 1 by columns, and similarly by rows. Ones on the main diagonal and zeros elsewhere. So notice that we're talking about the n by n identity matrix. So we are talking about square matrices. So a matrix is invertible. Sometimes a matrix does not have a multiplicative inverse, just like some real numbers don't have multiplicative inverses. In fact, only one real number doesn't have a multiplicative inverse. What real number does not have a multiplicative inverse? So 0 is the only real number that does not have a multiplicative inverse. So what we're looking for is a matrix is invertible. Let's say an n by n matrix. This is a thing that we're going to talk about for square matrices. An n by n matrix A is invertible if and only if there is an n by n matrix A inverse. So I'm going to write A to the -1, and that's going to be pronounced A inverse. That's how we're going to read that symbol, A inverse, such that A times A inverse is equal to the identity matrix, and A inverse times A is equal to the identity matrix. Which is a really great statement. A matrix is invertible if it has an inverse. It's like, well, yeah. But what that means is that if I multiply these matrices using matrix multiplication, I will always come up with the identity matrix. Not all matrices, not all square matrices have an inverse. Those matrices are called singular. An n by n matrix A is singular if A does not have an inverse, or if A is not invertible. So we would refer to 0 as singular because it does not have a multiplicative inverse. Any questions? All right. So the big thing that's going on here, and we got to think about, first of all, we need to spend some time in homework 2.1 practicing matrix operations, just adding them, multiplying by scalars, multiplying matrices, and thinking about that and practicing that skill so we can develop that. Then we spend the rest of the first half of chapter 2, so 2.2 and 2.3, we are talking about invertible matrices. And the big party piece of those sections is the invertible matrix theorem that has like 12 entries of the following are equivalent. And it talks about a matrix, an n by n matrix A is invertible, and then it lists all the things that are equivalent to A being an invertible matrix. It's row equivalent to the identity matrix. A is invertible if it has a pivot in every row and a pivot in every column. That means the columns of A span Rn. That means the columns of A are linearly independent. That means AX equals B has a unique solution for all B in Rn, and so on. There's like a whole list of things. The transformation X to AX, if A is invertible, the transformation is 1-to-1 and onto. So there's a lot of extra stuff that goes along with it. And it's a great example of a theorem of the form, the following are equivalent. So if you get one of those things, you get all of those things. If you are missing one of those things, you are missing all of those things. That's the power of the following are equivalent. Any questions? All right. Let's pause the video here and make sure that you're ready to finish out the week for chapter 1 and get started on chapter 2.